Hi, good afternoon. Welcome to lecture 28. We're starting to talk about compressible flow today, right? So getting into some complex topics in fluid mechanics. Let me share my screen. And we'll get started. Okay, so here we are. Today we're talking about compressible flow, and the foundation of compressible flow is ideal gas thermodynamics, right? So if, as we go through the material today, you feel like you need a little bit of a refresher on the fundamentals of thermodynamics, please go back to module 1 from week 1 of the course and go ahead and do the assigned reading there, the optional reading on thermodynamics background. But here we'll do a quick refresher about the quantity-specific heat, internal energy, enthalpy, and some other thermodynamic variables, including entropy, and derive a lot of really useful relationships. And then we'll also talk about stagnation properties, right? If you bring a flow to rest, you can write down expressions for the thermodynamic variables in terms of the flow that's at rest. All right, so jumping right in. If you remember, one of the very first relationships that we talked about in the course was the ideal gas law. And it tells us that the density is equal to the pressure over the gas constant times the temperature, right? So boxing it again, although we've seen it plenty of times before in the course, it's super important for what we'll be doing in this chapter. It's equation 11.1, but it's also equation 1.8, right? So here, in the ideal gas law, we have our gas constant R. We're used to just going to table 1.7 or 1.8 and looking this up. Just a little bit more specifics on what this is. So for a specific gas, the gas constant R is a universal gas constant called lambda, over the molecular weight for the particular gas. And that's how you get the gas constant for the particular gas. All right, but as always, we can just look up our gas constant R in table 1.7 or 1.8. Okay, the internal energy, U hat, is a function of temperature only for an ideal gas. So we can express CV, the specific heat of our gas at constant volume, in the following way. And what does this little subscript V at constant volume means? It means if the fluid undergoes a process, for example, the temperature changes, as long as we hold the volume of the fluid constant, this relationship holds. So we can simplify this like this. This is equation 11.3. So here we're changing the partials after the first equal sign to total derivatives after the second equal sign, because the internal energy is only a function of temperature. There's nothing else that you could take its derivative with respect to, so we can do this. All right, we can rearrange this and integrate it. And when we do that, we get the following. And if we now assume that this specific heat is constant, we can just integrate the right-hand side of equation 11.4 here. And we're also assuming no losses. So we have this expression, we'll use it a lot to calculate changes in internal energy in the state of a fluid. Between section 1 and 2, let's say, if we're looking at pipe flow, it's a reasonable expression, except it's only valid for moderate changes in temperature. Now, for the purposes of this course, we're going to always assume that CV is a constant, but just know in reality, it actually is somewhat dependent on the temperature. So we'll just make a little note. All right. Okay, moving on to our next thermodynamic variable, enthalpy. We can go for a very similar process to derive an expression for the enthalpy of a flow, or the difference in enthalpy from state 1 to state 2. But going back to the very fundamental definition, it is the internal energy plus this quantity P over rho, right? The pressure over the density, where we call pressure over density the pressure energy, okay? So what have we just stated? Just to summarize what we've said so far, we've said that the internal energy in an ideal gas is a function of temperature only. And if we look at this expression we just wrote down, we can see that P over rho, just rearrange it, that it's equal to, or pardon me, this is from the ideal gas law, P over rho is equal to RT from the ideal gas law. So it follows, looking at the expression we just wrote down, that the enthalpy is also just a function of temperature, right? Because the internal energy is, and the pressure energy are both just functions of temperature, and the enthalpy is just the sum of those two. All right, then as for internal energy, we can write down a very, very similar expression. It looks identical to the one for internal energy, except the constant is C sub P, not C sub V, right? So this is our gas constant when the process holds the pressure constant. This is equation 11.9, and just like for our previous expression that we derived, this is also reasonable for moderate changes in temperature. Okay, now if we combine equations 5 and 9, I'm going to write 5 and 9. This is really shorthand for 11.5, right? We obtain the following expression, right? So we're combining the basic definition of enthalpy as internal energy plus pressure energy, and we're using the ideal gas law. And now we can differentiate that with respect to temperature. And we get this expression. Now, if we consider equations 3, 7, and 11 that we just wrote down, right? Equation 3 is the definition of the specific heat at constant volume. Equation 7 is just our expression for our enthalpy, right? And 11 is what we just wrote down. We can conclude the following, that for every gas, the difference of the gas constants of the specific heats is a constant, right? So we know that R is a constant for a given gas. And now we've concluded that the difference in the specific heats, Cp and Cv, specific heat with constant pressure process, specific heat with constant volume process, is a constant, and it is in fact R. And it also shows us that Cp is greater than Cv, right? Because we know that R is positive, so we can see that Cp must be greater than Cv in magnitude. Okay, and then we define the specific heat ratio like this. And we're going to use this all the time in our thermodynamic equations. And as we just concluded, Cp is greater than Cv, right? So this is always going to be greater than 1, greater than or equal to 1. Okay, almost done with our derivation. We're going to combine equations 12 and 13, those last two we just wrote down, to get these expressions for our specific heats. And Cv is equal to R over K minus 1. (11, 14, and 15). So again, I just want to stress we're going to assume that Cp and Cv and K are constants in this class. But no, in reality, they depend a little bit on temperature. Okay, finally, we'll bring in our final thermodynamic quantity, the entropy. Entropy is a really interesting concept. Your textbook actually defines it as the property that doesn't change in a process with no friction or heat transfer. So I don't find that an incredibly useful definition, right? The property that doesn't change in a process with no friction or heat transfer, because it doesn't really describe or give you a sense of what entropy is. You can think of entropy as a measure of disorder in your system, right? So if you think of a fluid flow, if you have flow through a pipe and you've got flow in these nice straight lines, you can specify the position of every fluid particle at any given time, right? Imagine you've got uniform frictionless flow, right? So you've just got every single particle traveling along a straight line from left to right. You know what the initial location of the particles is, you know what the speed is, so you know where they are at every time. Well, then you add loss to the problem by adding friction at the walls. And then some of that particle motion near the walls gets dissipated. And we're sort of losing information about all of the particles in the system. It's becoming more disordered. Those particles near the wall may take a funny path to come to rest at the wall, right? So we've lost information about the position of the fluid particles in the flow, and the system has become more disorderly, and its entropy has increased when we compare the inviscid system to the viscous system. But let's talk a little bit about processes. So a reversible process is one with no friction. An adiabatic process is one where there's no heat transfer, no exchange of heat between the system and its surroundings. And if you have both of these, you have an isentropic process, so a process where there's no change in entropy. All right, the fundamental definition of entropy that's given in your textbook is this change in entropy as your fluid system undergoes some process from state 1 to state 2 is equal to the integral of the infinitesimal reversible heat added over the temperature. It's equation 11.16. It's outside of the scope of this class, the derivation of the next two equations I'm going to write down, but I did want you to just have the fundamental definition of the entropy in mind. This is a mechanical definition of entropy. If you're sort of a physics buff and you're looking for some fun reading, you can read up on the field of information theory and how they describe losses and entropy and information. And that was sort of spurred by these big telephone companies when they were trying to, design different cables. They thought in terms of, if you have a person on one end of a telephone line and you have the, person A, you have person B receiving what person A is trying to say, how much loss in the information do you have? And they associated that loss, they called it entropy, right? So there's this really interesting analogy between information entropy and mechanical entropy. It's pretty cool. All right, here I'm just going to write C section 11.1 for details and write down the following two expressions for changes in entropy. One in terms of the specific heat sub V and one in terms of the specific heat sub P. So in this equation, we've got the natural log, not log base 10. So here's our first equation for entropy, and our second one over here is in terms of C sub P. It's also in terms of a ratio of temperatures, but instead of having a ratio of densities, this one's got a ratio of pressures. And notice the subscripts have changed, right? In this equation on the left, it's rho 1 over rho 2. Over here on the right, it's P2 over P1. All right, so that's the end of sort of stepping through the thermodynamic quantities for compressible fluid flow. I've got an example next, but does anyone have a question about what I've written down on the last couple of slides? All right, so here we have air flowing steadily between two sections in a duct. So something like this. I'll write our control volume, draw it in here. We've got section 1 and section 2, and I'll just write flow. Over here we've got T1 and P1, the temperature and pressure at section 1 that are given, and we're also given T2, P2 in this problem, right? So air flows steadily. At section 1, the temperature is 80 degrees C. Pressure is 301 kilopascals. At section 2, the temperature has increased a lot. It's 180 degrees C, so it's been heated by 100 degrees Celsius, and the pressure has been decreased a lot, right? It's down to 181 kilopascals. And notice these are absolute pressure measurements, not gauge. All right, so calculate the change in internal energy U hat, enthalpy H hat, density rho, and entropy S between the two sections. And then maybe we'll talk about, depending on how long that takes, how we would estimate the loss of available energy. All right, so let's actually label these part A, B, C, and D. And we'll start with A. So we want to calculate the change in internal energy. Great, we just arrived an expression for this, right? So equation 11.5 tells us that U2 minus U1 is equal to CV T2 minus T1. Great, we're almost there. We have our two temperatures, right? We just need CV. So we also just derived an expression for that. So using equation 1115, CV is just checking the number. CV is R, our gas constant, over K minus 1. Okay, so we can go right to table 1.8 and look up R. I'm going to really go step by step in this first example so that you understand where every piece of information is pulled from. Okay, so table 1.8 for me, it's in the inside flap of the hard copy of the textbook. Tells us that the gas constant for air is 2.869 times 10 to the 2 joules per kilogram Kelvin. If you remember kelvins, those are our absolute temperature scale in SI units. It also tells us that K is equal to 1.4 for air. Right, so now we can go ahead and calculate CV. We've got 2.869 times 10 to the 2 over 0.4. And that gives us 17.2 joules per kilogram Kelvin. Okay, so we can go back over to our equation for the change in internal energy and plug in the values we've got. We've got 717.2 times T2 minus T1. I'm going to kind of belabor this point. T1 is equal to 80 degrees Celsius, but we cannot use static temperature in any of our thermodynamic relationships. We can't use it in the ideal gas law. We can't use it in any of the equations we've just derived. We must always use absolute temperature, right? So here we have to add 273 to get 353 Kelvin, right? And T2 likewise is given as 180 degrees C plus 273 is equal to 453 Kelvin, right? So that's the temperature difference we've got. So we get 71720 joules per kilogram. So that's our difference in internal energy between state 2 and state 1, right? Here at the left of this section, control volume, and at the right. So let's think about what's happening physically here. The flow is being heated, right? So it enters at section 1 at a lower temperature, 80 degrees C. As it moves to 2, it's at a much higher temperature, more than twice, at 180 degrees C. So it makes sense that the internal energy is a positive, the delta internal energy is a positive quantity. So that tells us the internal energy has increased as we've flowed from section 1 to section 2. Makes sense. All right, let's insert a blank page here. Just exit full screen for a moment to insert a page. And we'll go right back to full screen. Okay, so part A, what's the change in internal energy? Now let's move on to the change in enthalpy, part B. Okay, so equation 11.9 gives us the change in enthalpy. And it tells us that H2 hat minus H1 hat is equal to now C sub P, T2 minus T1. Let's go ahead and calculate CP. It's equal to K times R over K minus 1, according to equation 1114 that we just derived a couple of slides ago. Or it's equal to K times CV. So let's use this one because we just calculated CV. When we do this, it gives us 1,004 joules per kilogram Kelvin. All right, so coming back over here now, we've got C sub P is 1,004 joules per kilogram Kelvin times our temperature difference of 453 K minus 353 K. So this gives us 100,400 joules per kilogram. So we see that the enthalpy is also increased from section 1 to section 2 as the fluid's been heated. It looks like it's increased a little bit more. Right, it's got the same units. Notice the units, right? It's joules per kilogram. So this is per unit mass, right? This is a intensive property. And if you wanted to get, the quantity for the entire volume, you'd have to multiply by the mass. All right, moving on to part C. Oops, to blue. In C, we want to know what the density, change in density between sections 1 and 2 is. Good, finally, here's a quantity that we have some intuition about. Maybe this will be a little bit more interesting. So the ideal gas equation tells us that rho is equal to P over RT. And we can do this to evaluate the density at each section. So we can actually write rho 2 minus rho 1 is equal to P2 over RT2 minus P1 over RT1, or factoring out the gas constant R, this just gives us P2 over T2 minus P1 over T1. We can plug in some numbers here. So we've got 1 over 286.9 Newton meters per kilogram Kelvin, which is coming from table 1.8. Right. And then we've got 181,000 pascals, right? Newton per meter squared. So we're converting from kilopascals to pascals because that's the SI unit, over 453K minus 301,000 pascals over 353K. And this gives us minus 1.58 kilograms per meters cubed. All right, so this is kind of interesting. We get a negative change in density as we go from section 1 to 2. So what does that mean physically? And does it make sense? Right, section 1, got our air at 80 degrees C, gets heated as it travels to section 2. So how do we interpret the fact that rho 2 minus rho 1 is negative? Yes, density reduced, gas expands as it gets hotter, right? So exactly, it's negative, and that means that our density is less at section 2 than it was at section 1. It makes perfect sense. That's exactly what we expect from a gas, right? That as we heat it, it expands. So everything sort of checks from an intuition level there. All right, finally, section D here, we want to know about the change in entropy between the two sections. But let's just take a little moment to skip ahead to the next slide I've got here. So we just saw that the density decreased with the increase in temperature, right? And as I think it was Matt Kaida said, that's what we expect from a gas, and that's absolutely right. So if you look at this week's extra credit discussion problem, it's about Schlieren imaging. And this is sort of a shadow graph technique. It's kind of interesting. You can see a still from a movie that I posted here. And this is Joe Hansen coughing with no mask and coughing with a mask. And what you can see is the air exiting his mouth has got rapid variations in density. And you can see that because you can see the shadow that those different densities make, right? If the air were all one density, you would just see a uniform shadow projected onto the circle behind him, but it's not. There are changes in density. And that's because the air in his lungs is at a higher, right? Our internal body temperature is high. So the air in our lungs gets heated. And then when we exhale, when we cough, when we speak, it comes out and it's at a higher temperature than, generally speaking, than atmospheric temperature, right? So what you see is it's coming out, it's this turbulent stream, and so you've got this warm air and it's being it's being ejected into a cool ambient air bath, and you've got little sections of higher density, everything's sort of mixed up, a little bit chaotic. You've got small sections of higher density, small sections of lower density. It hasn't completely mixed yet and become uniform temperature. So just a little note. So if you're thinking of doing the extra credit problem for this week, it's just, which thermodynamic variable do you think is responsible for the changes in density? So if you came to this class, now you know the answer. All right, section D here, what's the change in entropy? We're doing on time. Okay. So we have the equation for the change in entropy that we just derived. It is equation 1124. We'll use this version. And it tells us that S2 minus S1 is equal to C sub P log T2 over T1 minus R natural log P2 over P1. Now, why are we using this version? Just because we're given the pressures, right? Makes it easy, although we could back it out from the densities too, because we've just calculated the difference in density, but it's a little simpler to use the pressures because we've got both those values at 1 and 2. Okay, so we've calculated all of these quantities in the earlier sections that we need, so we can just go ahead and plug them in. 1004 joules per kilogram Kelvin times natural log of 453 K over 353 K minus 286.9 Newton meters per kilogram K times the natural log of 181 kilopascals divided by 301 kilopascals. Now here it doesn't matter if it's in pascals or kilopascals because we're just looking at the ratio, right? It's going to be the same either way. And we get that it is 396 joules per kilogram Kelvin. Right. So that's our change in entropy. So from an intuitive perspective, this makes sense that we have positive change. We have an increase in entropy, right? Because the second law of thermodynamics tells us what? That entropy can never decreased. It can never be decreased, right? So we've got an increase. You can only have zero change in entropy or an increase. So we've got an increase in entropy, makes sense. Looking at the units, it's joules, which is a unit of energy per kilogram per Kelvin, right? So joules, but it's also proportional to how big your system is, which makes sense if you're thinking of the pipe example where we've got sort of entropy near the walls because the streamlines are sort of chaotic. And it takes more variables to describe the system from an information theoretic perspective. And it's also per K, per Kelvin. So that tells us that, that it depends on the temperature as well. And generally speaking, the higher temperature you have, the more entropy you have in your system. All right, I think in the interest of time, we're going to skip the optional discussion about how could you calculate the loss because it's beyond the scope of this class. I've got a little more I want to cover, but does anyone have a question about this example? I think it's pretty straightforward to calculate these problems. Just you must always remember to put both the pressure and the temperature in their absolute form and not use the static pressure and static temperature. Okay. So we're going to derive another set of thermodynamic quantities that are really useful because you can use lookup tables. And in our next section, we'll learn about the Mach number. And then these tables will become very useful. But stagnation properties, right? So we've talked about a stagnation streamline where a fluid particle follows it and comes to rest at a surface. We've talked about a stagnation pressure, which is the pressure in a fluid at rest. You can extend this concept to all of the thermodynamic variables. And in general, you can think of a fluid as having two types of states, right? It's got sort of its thermodynamic state. So, you know, what are the values of all of its thermodynamic variables? We've got listed out here the pressure, density, temperature, internal energy, and enthalpy and entropy, right? And then, you know, what we deal with more, at least in this class, is what's the mechanical state of our fluid system? What velocity is it moving at, and where is it positioned in a gravitational field? Does it have any elevation that's giving it potential energy, right? A really useful, and we sort of tend to think of these two states separately, but stagnation quantities sort of bring these together. They marry these two concepts of these two different types of states, and they tell us about the total state of the system, right? The mechanical plus the thermodynamic state. So what are stagnation properties? If you can imagine that a fluid were brought to zero velocity and zero elevation, like a snowflake falling on the ground, right? in some sort of frictionless process. So you don't do any work on it to make it do that, and you don't transfer heat to or from the system. It just comes to zero elevation, zero velocity, and you measure the properties there. Those are the stagnation properties. So we've got a little visual of this here at the top of the page. So here's a little fluid particle in state 1, and it's just zooming along with velocity v1. It's got some elevation z1. It's got pressure p1, temperature t1, entropy s1, right? And then somehow, without doing work on it, it's brought to rest at zero elevation. And now all of these properties have a subscript 0 for stagnation, right? Now you measure the properties, any property you measure with the particle here in this state, not moving on the ground, those are stagnation properties, right? So we can derive expressions for the stagnation properties by applying the energy equation to the streamline between states 1 and 0, or sections 1 and 0. And I just want to remind us back from chapter 5 that the loss, where we were talking about the energy equation a lot, the loss is defined as the internal energy out minus the internal energy in minus the net heat transfer in. So just a reminder. So if we apply the energy equation, we've got Q plus WS equals H naught minus H1 plus V naught squared over 2 minus V1 squared over 2 plus GZ1 minus GZ naught minus GZ1, where Q is Q net in over M dot, and WS is the shaft work done on the system, defined as positive into the system over M dot. Okay, so I'm just going to sort of say chapter 5 here. Just going back to when we derived the energy equation and the different forms of it. We did talk briefly about enthalpy and internal energy there. All right, but by definition, when the fluid is at rest, when the fluid particle is at rest on the floor, and we've brought it there by a process that is frictionless, exchanges no heat, and does no work, by definition, the heat in is 0. The work, the shaft work, or any kind of work is 0. Its velocity is 0, and its elevation is 0, right? So this simplifies a lot. In the following way. Now we're going to make the assumption that gravity and potential energy are negligible, and they almost always are for compressible flows. So we get the following form. So this is the stagnation enthalpy in terms of the enthalpy at point 1 when it was moving and at some elevation, but we dropped the subscript because this point 1, this position is arbitrary and the velocity is arbitrary. So it's true for any point in the fluid flow domain. So we just drop the subscript and we can relate the stagnation properties to the properties with the fluid particle moving anywhere in the flow field. All right, I'm not going to go through the derivation for all of the other quantities, but we can just write down our stagnation ratio quantities. And it looks like we'll probably not get to the second example, but I will write it out and upload it. All right, so the stagnation temperature, T naught is equal to T plus V squared over 2CP. Stagnation pressure. Now this is going to be a ratio in terms of the temperatures. And the stagnation density, also a ratio. This is equation 11.29, 11.30, and 11.31. I'm going to rewrite them in their more commonly used form that you get just by dividing these three equations through by T. And I will upload that, but I want to skip ahead because it's just about time to log off. And just take a brief look forward and take whatever questions you guys have. So, good news about midterm 2. Hyungan is done assigning partial credit for the problems. I am not done because I'm still considering dropping one of the problems. So the grades are not finalized. Even if you've received partial credit, your percent correct on the exam is not finalized. I expect it to be finalized today, and I will send an email out once it is finalized. Also, Hyungan is in the process of going through and sort of manually entering your grades so that they show up in the grade book, because right now you can see your grade on both midterms 1 and 2 if you go into the assignment itself, but you can't, it doesn't show up in grade book and doesn't show up in your grade calculation. So he's going to have that done by this week. It requires him to go through and all of those upload questions where you can upload your partial work. He has to enter zeros and then update the score, and he's got to do that for everyone. So it'll take a little bit. Here is the problems he's going to go over on Friday. This one, the starred one, is actually one of your homework problems. He's not going to solve it. He's going to set it up. It's an external flow problem about flow over a sphere that your lab instructor, Nick Johnson, asked me to go over, but you haven't had it in this class, so he's going to sort of give you the necessary background to solve that problem. So do I have any questions? We've got less than a minute left here. Do I have any questions from you guys about what we talked about today or looking ahead? Sure, I'll go back to the stagnation density. This slide or?
Yep.
Okay, great. All right. Well, it is 2:15, so I'm going to stop the class now. I'm happy to stay on. I'm going to stop recording. I'm happy to stay on in case anyone wants to ask any questions. Otherwise, thank you guys, and we will see you on Wednesday for more compressible flow content. Have a great couple of days.